In this video, we're solving a vertical freefall problem with two objects in it. So the setup for the problem is that we have one person releasing a ball from rest at the top of a building and a second person simultaneously throwing a ball upward. So that lower ball that's being thrown upward has an initial speed of 8.2 meters per second, and we're told the initial vertical separation between these two balls is 12.5 meters. And we go through a pretty standard set of questions here. First, we're going to figure out how long it takes for the two balls to run into each other. Then we compute the location where they collide with each other. And we're told to measure that relative to the initial position of the lower ball, which implies an origin here at the location of that ball. So there's our origin at the location of that lower ball. Now finally, we're going to get the magnitude of the relative velocity of these two balls when they run into each other. And the result of this relative velocity calculation is really special. We're immediately going to see that it's way too special to be a coincidence and try to get a deeper understanding of why it happened. And this leads us to reanalyze the problem in a free-falling reference frame to get some extra insight into the answer to that relative velocity question. So let's get all the standard calculations done in the stationary reference frame with the origin at the position of the lower ball. First, we want to find out how long it takes the balls to hit each other. And for this, we're going to describe the y-coordinate of each ball as a function of time using the standard kinematics formulas. So that upper ball, that's called ball number 1. So we'll say y1 is its y-coordinate. And that's equal to the initial y position, y0, plus v0 t, where v0 is the initial y velocity, and plus 1/2 at squared. So we know this thing starts from rest. In other words, v0 is equal to 0. And we'll go ahead and plug some numbers in here. So the initial y position is 12.5 meters. So we have 12.5. And then the acceleration, of course, is 9.8 meters per second squared pointing downward. So that's going to get a minus sign. And half of 9.8 is 4.9. So I end up with a 12.5 minus 4.9 t squared. Now we do the same thing for the second ball. So I have y2 is equal to its initial y position. That's going to be 0. And then initial velocity times time. This time it does have an initial velocity, that's 8.2. And we sub in that the acceleration is negative 9.8 again. So this time it's the initial y-coordinate that's 0. And I find that y2 is equal to 8.2t minus 4.9 t squared. And then the strategy here is to say, well, when the balls run into each other, y1 is equal to y2. They have the same position. So I set these two y-coordinates equal. And I get 12.5 minus 4.9 t squared is equal to 8.2 t minus 4.9 t squared. And those acceleration terms cancel out. This leaves me with just 12.5 equals 8.2 t. And if I divide 12.5 by 8.2, I get t. When I run the numbers on this, just keeping a little more precision than we normally do, I get 1.524 seconds. So next we want to compute the height where they collide relative to this origin at the initial position of the lower ball. And we can go back to either one of these equations that describe the y-coordinate of each ball as a function of time and plug in the t value that we found, and we should get the same height either way. It's actually wise to do both of them just as a check on your work. So we'll start with y1. That's the position of the upper ball that was dropped from rest. That's 12.5 minus 4.9 t squared. And we'll sub in 1.524 for the time there. When I run the numbers on this and round off to 3 significant digits, I get 1.12 meters. So this collision happens just 1.12 meters above the initial position of that lower ball. Hopefully, y2 gives us the same answer. So y2 is 8.2 t minus 4.9 t squared. And when I run the numbers on this to 3 significant digits, I do indeed get the same answer, 1.12 meters. That's a nice way to check our work. And it gives us a lot of confidence in this solution that the collision happens 1.12 meters above the initial position of that lower ball. Okay, so now we get into the calculation of the relative velocity when these two balls collide. So what we're going to do is write down the final velocity of each ball, and then we'll figure out the relative velocity. So we'll start with v1. And that's going to be the initial velocity plus acceleration times time. So v0 plus at. And the initial velocity for this guy was 0. And the acceleration, of course, is 9.8 meters per second squared downward. So we have a negative 9.8. And our time was 1.524. And we come out with a final velocity of negative 14.935 meters per second. Now we do the same thing for the second ball. Again, we just use that constant acceleration kinematics formula describing velocity as a function of time. And this time the initial velocity is positive 8.2. And then a is the same thing. So we have 8.2 minus 9.8 times 1.524. This gives us negative 6.735 meters per second. So one thing to notice here is that when these balls collide, both of them are moving downward. So that lower ball has already reached its maximum height and turned back around, and it's moving downward at 6.735 meters per second when it gets hit from behind by the second ball moving 14.935 meters per second downward. So they're both moving in the same direction. And to find the magnitude of the relative velocity, we just have to subtract their two speeds. And when we do that, we find an answer that's way too special to be a coincidence. The relative velocity is 8.2 meters per second, which is exactly the same thing as the initial velocity of that one ball that was thrown upward. So we've got to figure out what's going on here to cause something that's so big of a coincidence. There has to be a deeper underlying explanation. And one way to get clarity on it is to reanalyze this entire problem in an accelerating reference frame. In fact, we're going to take a reference frame that is itself in free fall. So here I put a downward acceleration of little g on our origin. Now, since each of these balls is itself in free fall, remember each of them has a downward acceleration of 9.8 meters per second squared, just like our origin does. We're going to see a zero acceleration on each of these balls from within this new coordinate system. So from within this new coordinate system, the final velocity of ball number one, given that it has no acceleration within the accelerating coordinate system, that final velocity is going to be equal to the initial, which is just zero. Same thing for the second ball. With no acceleration within these accelerated coordinates, the final velocity is just equal to the initial. And what's the relative velocity between a ball that's stationary and one that's moving 8.2 meters per second? Again, we get this answer of 8.2 meters per second. So that's the explanation of the coincidence. With both of these objects experiencing exactly the same acceleration, that relative velocity of 8.2 meters per second never changes. And it was just more clear to see this in a coordinate system accelerating downward in free fall. Now we can, in principle, answer the other parts of the question within this accelerated coordinate system. So if we look at part A, how long does it take these two balls to hit each other? We do see a distinct advantage to using this accelerated coordinate system. When I write down the y-coordinate for ball number one in the accelerating coordinate system where ball number one has no acceleration, well, this guy has an initial position of 12.5 meters above the origin, an initial velocity of 0, and an acceleration of 0. In other words, the y-coordinate of ball number one is always 12.5 meters above the origin of coordinates, provided the origin of coordinates is just in free fall, accelerating downward. We do a similar thing for y2. We have an initial location there of 0, but an initial velocity of 8.2. And again, an acceleration of 0, provided we're watching it from a free-falling reference frame. So we quickly here get the equation 12.5 is equal to 8.2t when we try to find the time that these balls collide. And that should be familiar. That's what our equation simplified to last time when the acceleration terms canceled out because the accelerations of both balls were the same. When we solve for t here, we still get 1.524 seconds. Finally, we can get the height at which these two balls collide. And all I'm going to do there is ask, relative to the external reference frame, the stationary reference frame that's not moving, how far down has my origin of coordinates moved? And we know the location of this top ball is always 12.5 meters above that. So we're really translating back into the external reference frame here when I write this down. I want to find out how much the vertical coordinate of my accelerating origin has changed. Well, its initial position was 0, its initial velocity was 0, and its acceleration is 9.8 meters per second squared downward. So I just get negative 4.9 t squared. This describes the location of our accelerating origin relative to our fixed origin. So we can sub in our time of 1.524 seconds. That's how long it takes before the two balls collide. And we find out that the location of our accelerating origin is now 11.38 meters below where it started. Well, we happen to know that ball number one always stays 12.5 meters above that origin. So to find the location of ball number one in the external stationary reference frame at the time of the collision, we take 12.5 meters minus 11.38 meters. And we find that same answer for the location of the collision, 1.12 meters above the initial location of the lower ball. So now we can compare these two approaches to the problem and ask sort of which one is better, or are there pros and cons to these two approaches? So just at a glance, we can take in sort of how much work was on this page, take in how much work was on this page where we did our original approach to it, and it looks like the accelerating reference frame approach was quite a bit simpler. Now I will admit that part B was a little bit tricky compared to the stationary reference frame approach, but the relative velocity question was clearly much easier in an accelerating reference frame, and the time for the collision was significantly simpler as well. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.